Alright, hello, we're back. And today we're going to be working through another physics proof. And this time we're going to do the proof of the final position. And let's go ahead and get started. Alright, so the final position proof that we're trying to prove is going to be this one. We have x final, or the final position, is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration in, I guess, the x direction, but it can be any direction as long as it's, one dimension, times time squared. It's 1/2 at squared, and we're going to try and prove that. So what we're going to do is we're going to start by saying, and this kind of applies for anything in physics, we have the final position is equal to the initial position plus the change in position. Right, and I think this can be very straightforward. If we have, we start at 4 meters, we go 5 meters to the right, right? So that's 4 plus 5, your final position is, 9 meters. This also works for velocity. If we're going 4 meters per second and we change, now we're going 5 meters per second faster than we were before. We're going now 9 meters per second. It works in acceleration, it works in velocity, it works in position. And so we're going to go ahead and start there. And I'm going to write over here. We also know that the change in position is going to be represented by delta x. We can say that is equal to the velocity times time, or the velocity average times time. And velocity average we know to be equal to the final velocity plus the initial velocity over 2. Right, so literally the average of the two velocities. Great, so if we substitute this back into our blue, we can say that the final position is equal to x initial plus the average velocity, so plus the delta x, which is here. We're going to use this over here, and then we're going to use this for average velocity times time. So we'll just say it's, I'm going to go ahead and write it not as a fraction, but as 1/2 times the final velocity plus the initial velocity times time. Right, so what we did here is we said that this is the kind of x position, or the delta x, so the final x equals the initial x plus the change in x, and the change in x was up here, the average velocity times time. All right, and let's say we don't know the final velocity, but we do know that the final velocity is equal to the initial velocity plus the change in velocity. Oops, I can draw a better velocity than that. We'll just say it's the change in velocity, right? And that just comes, directly from this equation, right? It works for anything, so it must work over here. So another way of writing this is saying that the final velocity is equal to the initial velocity. We can rewrite the delta v as the acceleration times time, right? Or the change in velocity times time. Just like we said, it's the change in position, the average velocity times time. We can write the change in velocity times time as acceleration times time. All right, so I'll go ahead and kind of remove those two arrows. And we can substitute it back in for our equation right here for this kind of final velocity. And I'll go back to blue. So we have the final position is equal to the initial position plus 1/2. And we're going to say 1/2 the final velocity, but I'm going to use this for final velocity. So I'll say 1/2 times vi plus at. That's final velocity. But this is final velocity, and we need to add this initial velocity and multiply the entire thing by time. All right, so we have our initial position. We have 1/2 this quantity here is this quantity here, where this is final velocity, and that is initial velocity, and we have our time here on the end. All right, now we can start, distributing the 1/2s. We can combine our like terms. So if we simplify, we can say that the final position is equal to the initial position plus, and again, so these are just at these three terms here, so here, here, and here, those are all adding, so there isn't really a need for the parentheses. So we can actually just combine that initial velocity and that initial velocity to 1/2 times 2 velocity initial plus acceleration times time, all times time. I think this is getting a little bit exciting. If you're not excited, then you probably, if you are excited, you probably have no life, but that's okay. I think it is really exciting, and this leaves us with, if we multiply in kind of this 1/2 here and here, we'll get initial velocity plus acceleration times time over 2 times time, or we could say the final position is equal to the initial velocity, or the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. That was what we were trying to prove in red up here in the first place. So there it is. We have the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. And that is where it all comes from. I think that's really exciting, and I hope that now we have a better, more intuitive sense of the way that this comes from, and it really all stems from, the final of anything, the final position, the final velocity is the initial plus the change, right? So that's true. Then we use this function, or that equation, so we have the final velocity is initial velocity plus change in velocity. And again, those are all true. And so that's kind of how we use that to build out this equation, and we got our proof kind of down here. Super cool. All right.